first example of how to solve a linear system of ODEs. We are going to stick to 2D examples for two reasons. One is they are less computations than 3D examples, but they work in the same way. And two, in 2D, it's easy to draw what we're looking at. We can draw phase portraits. Phase portraits are the idea that you're looking at the plane, R2, and you want to know where each single point of the plane moves towards through the ODE that you're working on. And you do that by giving some sketches of solutions. So the first example that I want to look at is x prime equals a times x, where A is a diagonal matrix. That means it has only non-zero values on the diagonal, with diagonal 1, minus 2. But this is a system we should be able to solve in a different way. For example, we can think of splitting this system in x1 prime equal x1, x2 prime equals minus 2x2, and solve these two independently. We have x1 as a function of time is a constant times exponential of time, and x2 is a constant times exponential of minus 2 time. So this is one way to solve this ODE. We split the two equations and we solve each equation independently. Then we can also do what we have talked about. We compute the eigenpairs. That means the eigenvalues first and the eigenvectors later of the matrix A. And this turns out to be a couple. The first eigenpair is 1 associated with the eigenvector 1, 0, and the second eigenpair is minus 2 associated with the eigenvector 0, 1. So now that we have this, we can write our solution x in a vector format as c1 multiplied by the first eigenvector 1, 0 multiplied by exponential of the first eigenvalue times time, exponential of t, plus c2 second eigenvector exponential of second eigenvalue times t. So c2 multiplied by 0, 1 exponential of minus 2t. If we put these things together, we retrieve that x is c1 exponential of t in the first component and c2 exponential of minus 2t in the second component. Note how these two are equivalent. With like the solution we got by splitting the example into two independent equations and the solution we got by solving straightforwardly are equivalent. And this is true in general. You might be able to untangle the two equations that you want to solve, but the solutions that you will get will be equivalent. So let's try to plot what we just found. That means constructing a phase portrait indicating where each single point in R2 is moving. So here we have x1 in the horizontal axis, x2 in the vertical axis. We have an equilibrium at their center because we know that the only solution of x prime equal ax that is in equilibrium is the origin. And we have the two eigenvectors that are horizontal and vertical. They're very simple. And we know that if x t0, so if we start at time 0 as a multiple of the eigenvector, then x at time t is still going to be a multiple of the eigenvector. What does that mean? It means that if we are a multiple of the eigenvector, so we are on the line along the eigenvector, we're going to stay on the line defined by the eigenvector. So this is why there are these two green lines. If we start there, we stay there. And the coefficient in front of the eigenvector is this c multiplied by exponential of rt. So if r is positive, this exponential increases over time. That means you're moving away from the equilibrium. If you start close to the equilibrium, on the right, you're going to be moving more towards the right. On the left, you're going to be moving more towards the left. The same if you're starting on the top or at the bottom. Either way, you will never go towards the equilibrium. You're going to go away from the equilibrium. If r is smaller than 0, that means that the coefficient in front of your eigenvector is going to decrease over time. So you start somewhere and you move towards the equilibrium. So for xi2, for the vertical eigenvector, your eigenvalue was 1. So we're going to move away from the center. For the horizontal eigenvector, I think I actually switched around the vertical and the horizontal. For the horizontal eigenvector, we had the eigenvalue -2. So we're moving towards the equilibrium. Now that we have an indication about everything on the horizontal axis is moving towards the equilibrium, everything on the vertical axis is moving away from the equilibrium, what is happening to a point that is not on either of the two axes? Well, x0 will be a sum of both eigenvectors. It's a linear combination of the first eigenvector and the second eigenvector. And we can uniquely define C1 and C2 such that it holds. So in general, if we start at x0, the solution passing by x0 is a linear combination of exponential of r1t times xi1 plus exponential of r2t times xi2. So over time, we have that we're pushed in the two directions, then the two eigenvectors are already pushed on. And we have something that goes towards the equilibrium, but actually the closer you get to the equilibrium, the slower you're going, and something that goes away from the equilibrium, and the further away from the equilibrium you're going, the faster you're going. So at the beginning, you're almost flat going towards the equilibrium. At the end, you're almost flat going away from the equilibrium, and you have a slope in between. We can do this discussion for every single one of the 4 sectors and retrieve these lines that give us the phase portrait. Is a rough understanding about where each element in the plane is moving. Let's look at a second example, a bit more complicated. We have x prime equal 2, 1, 3, 2 times x. We compute the eigenvalues by computing the determinant of a minus lambda I, where I is the identity. We retrieve that the eigenvalues are 1 plus or minus square root of 3. Now we compute the eigenvectors. I'm going quite fast, but all the information are on the slide. If you want to go slower, please interrupt the video and look at it a bit longer. We can compute the eigenvectors, and we retrieve that the first eigenvector associated with the eigenvalue 1 plus square root of 3 is the eigenvector 1 minus 1 plus square root of 3. And we can find the other eigenvector associated with the eigenvalue 1 minus square root of 3 being 1 minus 1 minus square root of 3. So we have the eigenpairs. That is just the combination of all the things I've said until this moment. The two eigenvalues associated with their eigenvector. So the general solution is a linear combination of eigenvector multiplied by the exponential of eigenvalue times time. So in this case, it's C1 multiplied by 1 minus 1 plus square root of 3 vector multiplied by exponential of 1 plus square root of 3 times time plus C2 vector 1 minus square root of 3 exponential of 1 minus square root of 3 times time. Check where each piece is going. And if we look at this, we retrieve that the first block has an exponential of 1 plus square root of 3 times time. This is positive, so it increases over time. The importance of this first block grows over time. While the second block has an exponential with coefficient 1 minus square root of 3. That is negative. It decreases over time. So for t big, the first element is important. For t small or even big and negative, the second element is important. So for t big, we're going to move as we only see the first block, so only the first eigenvector. For t small, we see the other one. So if we plug in an initial condition, for example, we want a times 0 to be at 3, 4, we want to find coefficient C1 and coefficient C2 such that at time 0 our solution is equal to 0, that means that the exponentials at time 0 disappear. We only have c1 times xi1, first eigenvector, plus c2 times xi2, second eigenvector, equal to the vector I just gave as initial condition. Is there a new unique solution? And why is there a unique solution? There is a unique solution. It's a 2 by 2 problem. That means we have two unknowns, c1 and c2, but two restrictions. We have the restriction given by the first line of this problem, that is c1, first component of the first eigenvector, plus c2, first component of the second eigenvector, equal first component of our initial condition, and the same for the second condition. And why does this system have a unique solution? Because we know that the first eigenvector and the second eigenvector are linearly independent. That means that the matrix constructed by the first eigenvector and the second eigenvector has determinant different than 0. So if we're building up a matrix form built on that, it's going to have a unique solution. So let's build a matrix form. We want the first component of the first eigenvector multiplied by c1. So we place 1 in the first block of our matrix form and c1 in the first value of our unknown vector. We want the first element of our second eigenvector to be in the second position of our first line of the matrix, and c2 as our second unknown. And we want this row of the matrix times column vector be equal to 3, the initial condition that we just gave. The same way we go for the second line, that is second component of xi1, second component of xi2, multiplied by c1, c2, equal the second component of the initial condition. And this, we can do multiple things, but either way, we can solve it as a 2 by 2 linear system. That will give us some value of c1 and c2 that depend on the step we just did. So the full solution is x times c1 that we just computed times xi1 that we have known times exponential of the first eigenvalue multiplied by t plus another coefficient, another eigenvector, exponential of the other eigenvalue times t. Notice how at some point we have chosen one specific eigenvector. We know that eigenvectors are defined up to a constant. So we could have taken something that is bigger or something that is smaller, something that is multiplied by -1. The choice we made determined the choice of c1 and c2 that we have found. If we had made another choice, all these steps would have followed in the same way, except the final result for c1 and c2 would have been different. So let's plot this. First step, we plot the two eigenvectors that we have found, v1 and v2. They all have x value 1 and y value -1 plus square root of 3 or -1 minus square root of 3. Then we draw lines extending these eigenvectors all the way. Then we remember the eigenvalues associated with these eigenvectors. So v1 had a positive eigenvalue, so v1 is moving away from the equilibrium in the center, while v2 had a negative eigenvalue, so v2 is moving towards the center. So the other values move partially like v2 towards the center, and then they start moving away from the center following v1.